In the previous lecture, we talked about what confidential computing is, why it's needed, and the different type of coprocessors that enable it. In this lecture, we are going to dive a bit deeper into trusted execution environments, also known as secure enclaves. Specifically, the different types that exist today, how they work, and what sets them apart. We'll also talk about some of the terms and mechanisms that are essential when working with trusted execution environments, or TEs for short, like remote attestations and reproducible builds. So without further ado, let's dive in. First up are remote attestations. So, what is it? And why does it even matter? Now, before we go into the technicalities, let's understand the term remote attestation. We'll start with remote. In simple terms, it just means something that is happening from a distance, like making a phone call to a friend in another city. You don't really have to be physically present near them to connect or share information. Attestation simply means proving something is true. It's like showing your school ID to prove you are a student, or a signature to prove that a document is legit. So when we say remote attestation, what we really mean is proving that something running far away on someone else's computer, in the cloud, or in our case a TE, is what it claims to be and that it's running securely. Now, in the world of TEs, remote attestation is the process by which a secure enclave proves a few key things. First, that the code running inside is authentic and untampered with. Second, that the generated remote attestation is recent and not from some old cached state. Third, that the attestation was generated by a real enclave running on a secure platform. And last but not least, the enclave is running an enclave image with specific PCR values. Let's talk about PCRs for a bit. Platform Controlled Registers, or PCRs for short, are measurements of an enclave's internal state, which also includes the code it's provisioned with, ensuring that what's running is exactly what you expect it to run. And where do these PCRs come from? They come from an enclave image file, or EIF for short. An EIF is a file, usually ending in a .eif extension, that contains everything to provision an enclave, a minimal Linux OS, all required libraries, along with your application code. Now that we understand attestations, let's talk about one problem that it doesn't address. Remote attestations do not tell us what specific code was used to derive an EIF. A malicious actor could have easily gotten hold of the system at the time of building an EIF. So now the TE runs a malicious build and is still able to provide remote attestations. Considering this scenario, a natural question arises. How do we actually verify that the EIF was built from a trustworthy piece of code? Because unless this issue is addressed, it becomes really hard for us to reason about the behavior of a TE. This is where reproducible builds come in. Reproducible builds give us a way to recreate a bit-for-bit identical EIF for the same given inputs. This solves a bunch of problems. First and foremost, it allows for attestation verification. This means that you can reliably verify the remote attestation itself against the actual code being run. Secondly, with reproducible builds, your code behaves the same way across different environments and machines. This means no more "it works on my machine" issues. Finally, it's resilient. Anyone, including security researchers, can recreate your exact enclave environment. That means more eyes on your code and fewer attack surfaces. So the takeaway is this. Remote attestations are powerful, but they are meant to be used alongside reproducible builds. Now, let's look at the first type of TE, the Intel Software Guard Extensions, or SGX for short. SGX provides process-level isolation by creating secure enclaves within applications. This shields sensitive code and data from the operating system, hypervisor, and other processes. The trusted computing base here is minimal, just the CPU and enclave code. So even if the OS is compromised, your enclave stays secure. SGX uses Intel's attestation service to allow third parties to verify enclave integrity through cryptographic proofs. It's great for sensitive operations like secure key management or privacy-preserving AI, especially in untrusted environments such as the cloud. But, like everything, it has some downsides as well. SGX is vulnerable to side channel attacks, and it has limited enclave memory, which can make running large workloads pretty difficult. Next up, we have the Intel Trust Domain Extensions, or the TDX. While SGX protects individual processes, TDX protects entire virtual machines. It provides strong security by isolating entire virtual machines and encrypting their memory even from the hypervisor. TDX has a slightly broader trusting compute base than SGX as it relies on the CPU and a few hypervisor components. But it supports more memory, has fewer development constraints, and is better protected against hypervisor based attacks. And just like the SGX, it also supports remote attestations. So you can verify what code is running inside your enclave. The TDX is ideal for legacy apps and secure cloud environments with minimal changes to the software stack. Finally, we have AWS Nitro Enclaves. These are isolated, secure compute environments inside AWS EC2 instances enforced by the Nitro hypervisor. They protect sensitive data by separating CPU and memory from the parent instance, with no persistent storage, external networking, or interactive access. It's like building a digital safe room. Attestations are cryptographically signed and can integrate directly with AWS Key Management Service, allowing for secure handling of secrets. Nitro enclaves are also processor agnostic, so they work well with Intel, AMD, and AWS Graviton processors. Some common use cases for AWS Nitro enclaves include securing private keys, tokenization, MPC workflows, and regulatory compliant data processing in industries like finance and healthcare. They're especially great options for teams already operating in the AWS ecosystem who want additional security with minimal setup.